I'm looking at pressure in fluids, why the pressure in a fluid, a liquid or a gas, increases with depth, and why things seem lighter in a fluid than they do out of the fluid. So let's look at why the pressure changes with depth to begin with. So let's look at a container of fluid, liquid, gas, doesn't really matter. Take an object submerged in that fluid, and it is some distance h below the surface. So what is the pressure acting at a depth h in the fluid? So let's work that out. Now, in terms of how we come to this formula, you don't need to be able to do that, but you do need to be able to use the result. So the pressure at this depth is, of course, the force at this depth on this area divided by the area. The force then that's acting on this area is the weight of the fluid acting on this area. So there is this body of liquid or gas above this area. That weight is pushing down on it. So the pressure is the force divided by the area, mass times gravity over the area. So how do we work that out? Well, that, of course, the mass is the volume times the density. We know that. So mass, volume times density, times gravity over the area. And of course, the volume is the height of the fluid, this h, times the area. If you think about it, what you have basically is, if we take this to be a cylindrical thing, object, you have the area, which is here, and you have the height here. So the volume of this fluid would be the height times the area, which is all I'm saying here. So the mass, volume times density, is density times height times area, and the weight, which is mass times gravity, is that. So you can see here we've got area on the top line and we've got area on the bottom line. So those areas can cancel, or rather those areas will cancel, and you end up with the pressure is density times gravity times height. So this is the formula that you need to use to work out pressure at a depth in a fluid. So a fluid density, rho, on a planet where gravity is g, meters per second squared or newtons per kilogram, at a depth h, the pressure will be that. So that's why the pressure increases with depth, because as this gets bigger, this gets bigger. This is why. So let's look at why things are lighter in water, or any other fluid for that matter. It's true for air, it's just that the difference is very small in air. But you can see that there is a difference in air. So let's go back to the diagram, but it's slightly modified. Same diagram last time, but slightly modified. We have the object in the fluid, density rho, at a depth. I'm going to call this H1 this time because I've got two depths, H1 and H2, for the top and the bottom surfaces. And overall, we want to consider the resultant force on this. So I've got the weight of the object in there too. So The pressure on the top face, like we did before, just worked out the pressure at a depth, rho times g times h1. Pressure on the bottom face, rho times g times h2. Now, h2 is bigger than h1, so the pressure on the bottom is greater than the pressure on the top. You have the same area on top and bottom, and so the force on the bottom must be greater than the force on the top. So we have a net upward force, the difference in the pressures, P2 minus P1, times the area. So because the force upwards here is bigger than the force downwards here, they don't cancel. And so there is a force upwards which is reducing the effect of the weight. There is now a smaller resultant force, P2 minus P1 times A, minus W. Now the algebra isn't terribly important. What's important is you see there is a force due to the pressure on this face. There is a force due to the pressure on this face. Because the pressure on the bottom face is greater because it is deeper, then there's a bigger pressure upwards here than there is downwards here. And so if you multiply both pressures by the areas, you get the forces. There's a bigger upwards force due to the fluid than downwards force, which means just thinking about the fluid, there is a net upwards force. Now if you bring the weight into it, there is a net upwards force due to the fluid, which reduces the effect of the weight. So now this object appears to have a smaller weight in this fluid than it had out of the fluid. Now the weight hasn't changed. The weight hasn't changed because the weight is mass times gravity. The mass hasn't changed, gravity hasn't changed, but there is an additional force now which has the effect of reducing the impact of the weight. So we have this resultant force on the object, which is the difference in the forces on the top and bottom faces minus the weight. So what that means, of course, is that if this difference in forces is equal to the weight, your object will float. There will be no resultant force. One final point to make about pressure in fluids. At a given depth, the pressure is the same in all directions. So if I was to take a nice simple diagram, if we were to take our fluid and we take an object, that's supposed to be a straight line. Let me make that a straight line so it's a bit clearer what I'm trying to say. So we have our fluid. There is, at this depth, there's a pressure in that direction. 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 And those are all the same at a given depth. Is the same in all directions.